Okay, then welcome to my talk. I will talk about identification over the Gaussian channel in the presence of feedback. This is a joint work with Holger Bocher, Raphael Labidi, and Moritz Wiese. So first, I want to remind you what is identification. Most of you perhaps know already, but just a reminder and an overview. Then I will present you the result of Alswede and Dück about identification in the presence of feedback of the discrete memories channel. And then I will present you our generalization to Gaussian channels. And somehow you will see that you get a surprising result because it's not a direct generalization, and we were also, first have had the wrong idea, but you will see it later. Let's start with an overview on identification. So identification is different from transmission. So, and what is the difference? The difference is that the receiver have a different question what you want to solve. So he asked, is M prime sent or not? So he's just interested in one message and want to know if this message is sent or not. Somehow he's doing an hypothesis test. So of course Alice don't know in what message Bob is interested. So she used an identification code, but she don't know in which message Bob is interested. And this identification idea was first introduced by Jajan. He introduced in a deterministic version, a deterministic encoding, where we don't use randomization, and showed that we can go over the rate of a transmission code. Then in 1989, Alswede and Dück had the idea that they used local randomization at the encoder here. And with this, they can show that then they have a big advantage compared to transmission code. They show that instead of 2 to the 2n times, 2 to the n times c, like Chen showed that this is possible to transmit, they show that it's possible to transmit 2 to the nc, where c is really the same like Chen have. That was somehow this paper get the best paper award and was somehow celebrated. And what here you see somehow the both pictures. So in change pictures you have the receiver goal. What is the message sent? What is the message sent? And the sender chooses the messages in the set here. You see we have here 2 to the nc messages in totally. And here you see when we change the picture in the Alswede case, so that means we use also local randomization, so we allowed randomized input. Then when we ask the question, is M prime the message sent at the receiver, then we can encode much more messages. Then we have this double exponential. Okay. So here perhaps is what I already explained to you. So the trick is somehow how to get this double exponential growth. Now let's look at one channel and one receiver. Is really that you have an overlap of the decoding sets. And then you introduce here some kind of extra error that's called the second kind of error. And of course, you cannot do really transmission because you want that the receiver do an hypothesis test. So he asks if the message is in the set or not. And then you want that the error of the second kind is also small. And of course, you cannot do somehow really a decoding strategy because you don't know what you have to do if the message here, because then you need some decision. So you cannot translate somehow. You cannot use an identification code to do transmission. What you can do, which is done by Bringer, for example, is somehow some pre-processing, that you first do identification feedback somehow something and then go do some transmission. That's somehow where identification can help transmission. But that's not I want to talk about this today. I want to talk about just this model of identification where you really want to know if a message is sent or not and where you have feedback. So that's the next point. Now we assume that we have noiseless feedback. That's also very special. So first we look at the case, that's the most easiest case, that you have noiseless feedback. And this was already done by Alswede. So that means you send a symbol and then you directly, so it's also passive, so the decoder cannot use it to send something back, but the encoder always sees what the receiver have received. And so he can use this in his encoding strategy. That's the reason why now we don't have a code book, but we have this function here, which always depend, of course, on the message and also of the t-1, let's say, symbols or bits, which were received by the decoder. And I will present you now the what is known and then the extension to the Gaussian channel. So what is known? So with CIDF, we denote the identification feedback capacity. And with C of W, we denote just the transmission capacity. That means that's the channel capacity in principle of the discrete memory channel. Then if you look at the result, you get the following result, so that the identification feedback capacity is equal to the maximal X, and you have here the entropy of the channel if the channel capacity is positive. But we look, so Alswede and Dück, they look here at this double exponential thing. So they look at 2 to the NR. So the rate is defined already double exponential. Then you get this result. So that means if you can transmit something over the channel, then you get this double exponential result. And remember, we don't use local randomization. What we do here in our picture is just we use deterministic encoding. That means we cannot use any randomness for the encoding. And then we ask ourselves, what happened if we have now a Gaussian channel? And our first thought, we got a strategy, and our strategy was just that we have to replace here the entropy with a differential entropy. And we can prove that this strategy worked. And then we were, for 1 and 2 months, we were trying to find the converse. So here for the discrete memoryless channel, the proof of the converse is very easy because it's just somehow a combinatorial argument in the Gilbert-Bashamor things. You just count and then you can estimate and everything works. You just have to count how many decoding sets you can include and estimate it very roughly, and it's a very simple and nice proof. But we were not able to generalize this for the Gaussian channel, and we were very sure that our direct way was correct. And so we have a seminar and we give this talk, explain our strategy, and we learn a lot about packing for continuous variables, and we look at many papers, but we can't get a solution. So I just want to tell you the story why we cannot find the converse. So after fighting for the converse, if you have the differential entropy, then Moritz came. So Moritz Wiese, who is now co-author of the paper, and he gave us something. He said, "Are you sure that your direct proof is correct?" So it was correct, but are you sure that this is the best? And it turns out that this was the right question, because our generalization of the direct proof was somehow not good enough. And that's what we find out. Independently how we choose the rate, you can even choose that we want to have 2 to the n times r. then it's still steep infinite. So let's see. So first, the thing is here what we have in transmission, feedback does not increase the capacity. And what Alswede shows is we get a double exponential growth if we use it in identification. And somehow what you also see, noise decrease normally the transmission capacity, and here noise increase the identification capacity. And we discussed it already. The reason is that we can then generate common randomness. That's the main idea. Now, what is really the result for the Gaussian channel? Now we want to generalize this for the Gaussian channel. And we looked at this Gaussian channel here, and in principle at the same problem. And the result is we look at a deterministic identification feedback code, so such that lambda 1, that's the error of the first kind, it's the same like the transmission error, and the error of the second kind, that's this overlapping error. And then we can show for this, then if we use this double exponential growth, then we can show that the identification capacity is somehow infinite. So we have a power constraint, and we show that it's infinite. But we can show more. What we show that's a special thing. Then the reason why we look then at special scaling is because for the deterministic identification for the discrete members channel, it turned out, if we then generalize this to the Gaussian channel, it's in between somehow. If you use the scaling like Shannon did, then the capacity is infinity. But if you use the scaling like Alswede did, in this case without feedback, then the capacity is 0. And that's another paper we have. You have that the right scaling somehow is 2 to the n, and then you have to add a log n inside this. So it's in between 2 to the nr and 2 to the 2 to the nr. That's the scaling. And so we ask ourselves, is here also such kind of scaling such that that the capacity, if you choose the scaling, is also not infinity? And the answer is no. There's no such scaling. So here you see again so it's a little bit other displayed. So in the case, if you look at deterministic identification without feedback, you have to use the scaling n to the nr to get a positive capacity. If you use 2 to the nr, then the capacity goes to infinite. And if you use like Alswede did 2 to the nr, then it goes to 0. That's the reason why we ask ourselves, is there another scaling here? And sorry, that's the next result. Independent of the scaling, we always get an infinite capacity. And the idea of the proof is somehow that really you can create infinity common randomness, because you have this assumption. Now it's very clear when you know the result and you know how identification goes. Then I think it's very clear, because you just send one bit over the Gaussian channel, which is noisy. So we then, of course, and you feed it back to the receiver. And with this, you can create just with one symbol infinity many common randomness. And the idea of Alswede was how we use identification. We use identification by using such hashing functions. So we have each message somehow, each identification message belong to such a hashing function. So we have a ground set here, and this ground set is somehow created by the common randomness. And if you have infinity many common randomness, you can put here any value that you want, and you map this to a coloring set, to some finite coloring set. And what do the receiver do? Who is interested in message I? He completely knows this function here. So we do it for some value. We choose some L here. We can choose it as big as we want. You give me one. And then we create for every identification message, I create such a function here with a hashing. And then, of course, what is done by by the receiver and the encoder, because they have this common randomness, they randomly choose one of these elements here in this set here, and then in the rest, this common randomness is created just by the first symbol we send, and the other symbols are used to send the coloring. And the receiver, what did he do? Because of the common randomness, they both know which is the number chosen here in this set. And then he just decode the coloring. And then he checked if it is his function which is evaluated. So he just decodes somehow the color here. And then he knows, because of the common randomness, the color number, and he evaluates his function, and if it's the right color, then his hypothesis test say, yes, it's my message. That's the main idea of identification. And the trick here is really that with one bit, because we have this not realistic assumption that the feedback is noiseless, and we have a Gaussian channel which is noisy. That means just by sending one bit, we can create infinite common randomness, and this we can use to do identification. That's somehow the main trick. So here's again what I explained to you. We send some symbol, let's say it's a symbol 0 over the forward channel. We generate the random variable, we call it here y tilde, and we use it to compute this RID. That's it's just the set with this L I explained to you, and then we can create some identification feedback code with this. And yes, this is somehow the surprising result. Perhaps not so surprising if you know the proof, that independent which scaling I use, I can say I can have 2 to the 2 to the 2 to the n times r. I always get infinite capacity, and that's somehow that's really because the assumption here is unrealistic of having a noiseless feedback link and this noisy Gaussian channel. That's somehow the trick. And here, for example, there's an example. If you use, for example, this 2 to the 2 to the 2 to the nr scaling for the function, we still get infinity capacity. So we still get that the capacity is infinity, and still the error of the first and the second kind goes to 0. So the conclusion, somehow we provide a coding scheme that generates infinity common randomness between sender and the receiver, and we prove that the deterministic identification capacity is infinite, even if you use deterministic encoding, regardless of the scaling. That means even if you use localized randomness, of course, we cannot increase the capacity. It's still infinite. And future works, of course, we have to go away from this unrealistic assumption that the feedback is noiseless. So we have to look at noisy feedback and then see what can be done and what kind of assumption we have over continuous channels. Okay, then thank you, and I hope it was clear what is happening and how it works. So otherwise, please still continue asking questions.